Good afternoon, everybody, and welcome to the Subramaniam Chandrasekhar lecture by Professor Dam Son. The Subramaniam Chandrasekhar lectures is a series of the International Center for Theoretical Sciences of the TIFR, and they are delivered by eminent academicians on important new developments in their areas of specialty. The first lecture in any series, as the lecture today, is aimed at a general scientific audience, while the remaining are actually a little bit more technical. Usually, what we have found very fruitful is that around the theme of the lectures we have a small discussion meeting, which is also going on. We've had a very eminent set of people actually giving these Chandrasekhar lectures, so I should perhaps recount that the first one was given by Ashok Sen on extremal black holes in string theory. Then there was a talk by Andy Strominger early this year on black holes, the harmonic oscillators of the 21st century. Then Lyman Page talked about the standard model of cosmology. A short while ago in November, we had Ludwig Faddeev talk about modern mathematical physics. And the last one actually was by Subir Sachdev on the quantum phases of matter. So black holes seem to be sort of pretty... were mentioned by almost all speakers except by Faddeev. And today's speaker, Dam Son, is going to talk about applied string theory. Before I request Shiraz Meenwala to introduce the speaker, I'd like to request Professor Mustansir Barma, our director, to present a bouquet and a certificate. Shiraz, please.
Okay, so it's my pleasure to introduce Professor Son, the Chandrasekhar lecturer for today. Professor Son was born in Hanoi in 1969. He did his undergraduate studies at the Hanoi National University. He went on to obtain his PhD degree from Moscow University in 1993 at the age of 25 years. He's presently a senior fellow and professor of physics at the Institute for Nuclear Theory, University of Washington at Seattle in the US. Professor Son has made important and sometimes path-breaking contributions to many areas of theoretical physics, including the study of color superconductivity in QCD, the study of graphene, properties of graphene, properties of cold atom systems, particularly near their scale invariant point, and of course the study of the viscosity of strongly coupled fluids using the techniques of string theory and gravity in black hole physics. In this context, Professor Son made, along with his collaborators, Polycastro and Starry Nets, discovered that a large class of strongly interacting systems have a universal viscosity to entropy, a universal and low viscosity to entropy ratio that has been this fact and the general idea that you apply the ADS-CFT correspondence to the study of fluid dynamics has been very influential in the field of string theory and has guided the research of several people, including myself and several of my colleagues here at TIFR. Okay. Just before I end, I just give my a personal opinion, a personal feeling for Professor Son. In my opinion, Professor Son's work combines a high degree of technical accomplishment and creativity, along with a very wide knowledge of and appreciation of a wide range of physical problems in many areas of physics, that to me is sort of reminiscent of an earlier generation of physicists, perhaps like Landau, whom I think Professor Son has whose books Professor Sohn has studied very thoroughly. So I'd like to welcome Professor Sohn and request him to deliver the Chandrasekhar lectures.
It is my great honor to give a Chandrasekhar lecture today. When I was small and started to become interested in physics, the story of the voyage of Chandrasekhar to the UK made a very deep impression on me and was a great encouragement for someone who was growing up in a developing country, and I believe it's also a very big encouragement for many other people. I'm going to talk today about applied string theory, going from viscosity to black holes and quark gluon plasma. So the plan of my talk is the following. First, I will remind the audience about the notion of viscosity, and then I will mention there is an experiment on heavy ion collisions and the search for the quark gluon plasma, and then I will go to a similarly very different topic of gauge gravity duality, which is a very surprising, powerful byproduct of string theory, which then can be applied and hopefully, and as we will see, may tell us very interesting information about the quark gluon plasma. The notion of viscosity was introduced into physics a long time ago, in the beginning of 19th century by Claude Navier. He wrote down what would be later called the Navier-Stokes equation. Here is the definition of the viscosity. Suppose I have two plates, and between these two plates is some gas or liquid, some fluid. And then I try to move one plate with respect to the other. Then I would have to overcome a friction force, and that friction force depends on is a product of three parameters, two of which are purely geometrical. The friction force is proportional to the area of the plate, of course, and it is proportional to the gradient of the velocity. That is how quickly the velocity changes as one goes from the lower plate, where the velocity of the fluid is zero, the fluid tries to be at rest, to the upper plate, where the velocity of the fluid is the velocity with which we move that upper plate. But in this formula, there is one quantity, eta, that is an intrinsic property of the fluid. If one does this experiment with water and oil, for example, we would have different values of the friction force. That is because the different liquids have different values for eta. So eta is called the shear viscosity, or for short in this talk I will call that the viscosity of the fluid. Gas, we can do this experiment with water. We can also make this experiment with air. For dilute gases, the first theory of the viscosity of gases was constructed by Maxwell. At the time of Maxwell, the kinetic theory of gas wasn't an accepted theory. The existence of molecules is still a hypothesis. So Maxwell, working with the kinetic theory of gases, figured out that the viscosity is due to the collision between the molecules of the gases. In the terminology that we would be using right now, the hydrodynamic equation, which was written down by Navier and then Stokes, appears as an effective description that is valid over a length scale much bigger than the average distance that the molecule travel between two collisions, also called the mean free path. If we look at the gas at the distance is much bigger than the mean free path, we would see a continuous medium instead of a collection of point dive particles. And Maxwell gave an estimate for the viscosity of a gas, which is like follows. The viscosity is proportional to the product of three quantities, rho, V, and L, where rho is the mass density, V is the typical velocity of a molecule in a gas, and L is the mean free path, the mean distance between two collisions of a molecule. As a consequence of this formula, Maxwell observed that if one fixed the temperature and changed the pressure of a gas, then the viscosity should remain constant. And it is very easy to see. If we reduce the pressure of a gas by a factor of 2, then the density would be reduced by a factor of 2. Rho goes down by a factor of 2. But since the gas is now more dilute, it takes more length for a molecule to travel in order to find a particle to collide with. And using a very simple geometry, we can see that the mean free path grows by exactly the same factor of 2 with which rho decreases. If the temperature is fixed, then the velocity of the molecules is fixed. So this formula tells us that the viscosity of a gas does not depend on the pressure if we keep the temperature fixed. And that was something that seems to Maxwell very counterintuitive. And even now I find that fact rather strange. The viscosity at the intuitive level, we think about that as a measure of the thickness of a medium. If we make the gas more dilute, the viscosity should go down, but according to this formula, it remains the same. So Maxwell wrote the following. So Maxwell then went to Stokes and then asked the question about whether there has been any experiment that confirm or contradict this fact, and Stokes told him that he knew about one experiment that seems to say that the viscosity of air depends on pressure. So in 1860, Maxwell wrote the following. Such a consequence of a mathematical theory is very startling, and the only experiment I have met on the subject does not seem to confirm it. And that experiment Maxwell referred here is an experiment that was mentioned to him by Stokes. So for some time, Maxwell was very skeptical about the validity of the kinetic theory of gas as the theory of that described nature. But then he has the second thought, and within the next few years, Maxwell did his own experiment with the help of his wife. He constructed an apparatus that still exists now in a museum, I think, and he reported the result in 1865, that is 5 years after he wrote the sentence quoted in the previous transparency. The result is that the viscosity of air is independent of the pressure of air when the pressure of air varies from 1/60 of an atmosphere to 1 atmosphere, that is by almost 2 orders of magnitude. So Maxwell, the experimentalist, confirmed the prediction of Maxwell, the theories. That's something that I think is very rare in the history of physics, that the same person experimentally could predict his own prediction. So before going further, let us pause a little bit and talk about counterintuitive behavior of the viscosity. That is, the viscosity diverges when the interaction is turned off. When we make the interaction between molecules weaker and weaker, the mean free path of the molecule becomes longer, and according to Maxwell's formula, the viscosity should go up. Okay? But then we encounter an apparent paradox. If we completely turn off the interactions, then a gas becomes a free gas with no interaction at all. And usually we think about a free gas as a medium with no dissipation at all. So why is the viscosity goes to infinity, as Maxwell's formula tells us, but not to 0? And the reason is that we are implicitly talking here about two limits that do not commute with each other, that we have to, that are very subtle. One limit is the limit when we turn off the interaction, the limit of infinitely weak interaction, And another limit that is implicit in our discussion is the hydrodynamic limit of macroscopic distances. The hydrodynamic limit basically is the limit where the size of the apparatus, the distance between two plates in the experiment, is bigger than the mean free path that the molecule travels. So in order to measure the viscosity as the interaction strength going to zero, we have to, at the same time, make sure that the size of our apparatus is bigger than the mean free path. So that was, for example, if we try to measure the viscosity of a neutrino gas in the universe, relic neutrino gas in the universe, we would have to construct an apparatus of enormous size. So there is actually no contradiction between the fact that there is no dissipation at zero interaction and the fact that the viscosity goes to infinity when the interaction is turned off. But still, it is sometimes it feels like a very counterintuitive behavior, and it is related to the previous counterintuitive behavior that Maxwell encountered. Okay, now let us talk about the viscosity of liquids instead of gases. Liquids is a very dense state of matter. It's much more difficult to understand than viscosity than gases. By looking at this table that I just copied from a textbook in condensed matter physics, we can see that the viscosity of liquids changes by many orders of magnitude for liquids that in the very zeroth approximation would, from the point of view of string theories at least, would look the same. We have approximately the same density as the density of water, but the viscosity can change by many orders of magnitude. Let me also show you the viscosity of one particular substance, liquid glycerin, that behaves in a very interesting way, that if one changes the temperature by less than a factor of 2, the viscosity can change by almost 4 orders of magnitude. So the viscosity of liquids is can change by a large factor. And the liquid viscosity can be very large. There is one experiment called the pitch drop experiment that claims to be the longest continuously running experiment in the history of physics. In 1930, in University of Queensland, someone poured tar on top of a funnel and just let it sit there. Tar looks like a solid in normal circumstances, but if one wait long enough, then tar would flow like a liquid. And since 1930, there has been 8 drops falling to the cup. I read that no one actually witnessed the moment when a drop fall down. After the 7th drop, the university installed a camera to capture the moment of the 8th drop fall, but the camera malfunctioned, and nobody actually observed even the 8th drop. The viscosity of this star was estimated to be 10 to the 11 times of water, and the experiment was given an Ig Nobel Prize in physics. Okay, Edward Purcell, who, as one might recall, was one of the originators of nuclear magnetic resonance, was very interested in the question of why the viscosity of glycerin changes by so many orders of magnitude, while if one look at that from using nuclear magnetic resonance, it seems that nothing changed. So he posed this question. He thought about challenging Weisskopf, a theoretical physicist very well known for being able to explain everything in terms of fundamental constant of nature, to explain the nature of liquid viscosity. So we can read about Purcell challenge Weisskopf in a paper that became very famous. The paper is called Life at Low Reynolds Number, was published in American Journal of Physics. Mostly this paper deals with the question of how bacteria swims in a viscous medium. But in the beginning of the paper, Purcell poses the question of liquid viscosity to Weisskopf. But he anticipated that Weisskopf as a theorist would explain the large range of variation of the viscosity by reducing it to saying that it is an exponent of something that changes a little, like the standard way theorist would explain a hierarchy of quantity. So he added the following to the puzzle. But it's more mysterious than that, Vicky, because if you look at the chemical rubber handbook table, you will find that there is almost no liquid with viscosity much lower than that of water. The viscosity have a big range, but they stop at the same place. I don't understand that. That's what I'm leaving for him, that is for Weisskopf to explain. So, there is a puzzle. The puzzle is the following, that viscosity of liquid is unbounded from above, but seems to be bounded from below. As you see, tar can be a very viscous fluid, and there are many examples of very viscous fluid, but it seems that the viscosity is bounded from below by some quantity. So in this talk, I will not try to answer the Purcell's puzzle about the viscosity of real liquid, but I will try to formulate a version of the Purcell's question. Suppose we have a gas, and we can play with the interaction strength between molecules. Can we make the viscosity all the way going out to zero in a simple system of just molecules? And in the model context, that question is very important for the physics of the quark-gluon plasma, which we will see why it is important later. But let me now mention what is the quark-gluon plasma. So the quark-gluon plasma is the goal of a series of experiments, and one of the most recent experiments is conducted at the relativistic heavy ion collider at Brookhaven National Lab, and there has been also the heavy ion experiments at the LHC recently. At Brookhaven National Lab, the collision happened at energy of 200 GeV per pair of nucleons, and the ions are gold. The 200 GeV means that the ions are accelerated to a gamma factor of 100, to a very ultra-relativistic energy. So when two very highly energetic gold atoms collide, we would see the creation of many, many particles, as this reconstructed event at the star detector at Rick show you. So if we extrapolate all these particles to the initial time, we will see that all these particles was created in the very beginning in a very small region of space, and there was a huge energy in unit volume in the beginning. So we can hope to create and study a very dense state of matter called the quark-gluon plasma. Okay? So what is the quark-gluon plasma? Let us recall that hadrons that are like proton, neutrons, or particles like mesons, pions, for example, consist of quarks. For proton and neutrons, these are 3 quarks. Proton and neutron can be thought of as a back of 3 quarks, and pions as a back of an antiquark and a quark. If we put these particles together, we can have 2 regimes. If we have a dilute gas of proton and neutrons, then or these mesons, then we would have a situation where our gas can be thought of as a dilute gas of these bags. Each of the bags contain either 3 quarks or quark and an antiquark. This state of matter is called a hadron gas. But if we try to put more and more a particle in a volume, they start to overlap. When they overlap, it's no longer feasible, it's no longer useful to think about the state of the system as a collection of bound state. It's more useful to think about that as a collection of the constituent quarks and also the particles that they exchange that are called gluons. So the quark-gluon plasma is a state of matter that was predicted to occur when we have a very high density of matter very many quarks and gluon in a unit volume. The quark-gluon plasma can be thought as a state where quark and gluons move relatively freely. In fact, the theory of strong interaction is known. That is called quantum chromodynamics, or QCD, and people have been trying to study the phase diagram of QCD. So here I'm reproducing here a version of the phase diagram of QCD, of quantum chromodynamics. The region here, when the temperature is low and the baryon chemical potential is low, the baryon chemical potential basically measures the density of baryons. When both of them are low, we have the dilute gas of these bags, and it is the hadronic phase. And if we go to the regime where the temperature is high, when there are a lot of particles in a unit volume, you get to the state that is called the quark-gluon plasma. A lot of studies using lattice QCD has shown that there is probably no phase transition between the hadronic phase and the quark-gluon plasma phase. They separate by a rapid crossover, but there is a qualitative difference between quark-gluon plasma and hadronic phase, as we mentioned previously. This part of the phase diagram where the temperature is low but the chemical potential is high is rather controversial, and there is a lot of study and this is much more difficult to study. Okay, so the quark-gluon plasma was, as I mentioned, was the goal of a series of experiments. It turned out that unambiguous identification of the quark-gluon plasma is very difficult. The reason is that if the state of matter, if it was created, lived for a very short time. You create a medium, a very hot medium in a very small region of space, then it's basically explode, cooled down, and what is observed is just the particles that are the decay product of the initial hot medium. However, it is now a consensus between theorists and experimentalists that at the relativistic heavy ion collider we have created some strongly interacting medium. There are basically two main evidences. One evidence is the so-called suppression of back-to-back jet correlations. If we take the collision of two protons, in many events we would see a pair of jets that are coming out in opposite direction. But in a heavy ion collision, in many cases we see only one jet that come out. And the most likely explanation of that fact is that there was actually two jets, but one jet has to travel a long distance through the medium, and when it came out here, it has already lost all the energy. So the existence of this medium explains the fact why in many events we see only one jet. And another evidence of a medium is the elliptic flow. That is the signal that particles push each other, and I will talk more about this elliptic flow in a later part of this talk. So let us assume that at the relativistic heavy ion collider we have created some thermalized medium. We can ask the question, can we compute theoretically the viscosity of that quark-gluon plasma that was created? Why we want to compute the viscosity, I will mention that later. The viscosity determines how the droplets of this liquid expand. Right now, let's think about this problem as a theoretical challenge. There is a good side of this problem. The good side is that the fundamental theory is completely known, that is quantum chromodynamics. But the bad side of this problem is that perturbation theory doesn't work. Perturbation theory is something that we use in quantum field theory to compute quantities by expanding it in Taylor series. In the case of quantum chromodynamics, the expansion parameter is the coupling constant of QCD called alpha S, and that constant depends on the energy scales. At the relevant energy scale of the relativistic heavy ion collider, alpha S is of order 1. So there is no small parameter we can use to do calculation. And this is one example of how the perturbation theory works in practice. If we compute the pressure of quark gluon plasma to the 0th order, we get the Stefan Boltzmann pressure. That's just a pressure of an ideal gas. So we can ask what is the deviation from the ideal gas. So P over P naught, and let me try to compute this ratio at a temperature typical of heavy ion collision, that is twice the temperature of crossover between hadron gas and quark gluon plasma. We see that the 0th order, of course, is 1, and then the leading order in alpha S, we get something small, 0.2, but all the next terms also, doesn't show any convergence, doesn't go to 0. And in fact, so this graph tells you different bands correspond to trying to incorporate next further terms in this series, and they don't converge to a well-defined result unless we go to astronomically high temperature, unachievable in experiments. So what we can do, so with the viscosity, one expects even a worse convergence. There are evidences from calculation that for the viscosity the convergence is worse. So what we can do, we can try to measure the viscosity experimentally. Unfortunately, right now, I don't know any theorists that can do that experimentally. So we are not in the time of Maxwell. And as theorists, we can take another approach. That is, we can try to find the viscosity in the simpler theory and then try to extrapolate to QCD. And that simpler theory appears very unexpectedly from a different corner of physics, string theory. And the technique that is relevant for this problem is called the gauge gravity duality. In 1997, Maldacena considered a very abstract object in string theory called the stack of ND3 branes in type 2B string theory. We don't need to know a lot of details about this. I'm going to try to explain it in picture. What is the observation by Maldacena? Maldacena observed that this object that I was trying to depict here as the set of soap bubbles, the D3 branes can be thought about as the three-dimensional soap bubble in a nine-dimensional space. This object can be described in two different pictures. In one picture, it is described as a quantum field theory, very similar to QCD, but different from QCD in detail by a quantum field theory called N=4 super Young-Mills theory. So this set of soap bubble can fluctuate, and the fluctuations are encoded in some quantum field theory called N=4 super Young-Mills theory. But Maldacena found that the same object in string theory can be described in a completely different way. That is as a string theory in a curved space-time. A string theory living in 10-dimensional space-time called ADS5 cross S5, where ADS5 is the anti-de Sitter, 5-dimensional anti-de Sitter space, a space with constant negative curvature that I was trying to depict here, times a sphere. So this is a striking equivalence between very different theories. One theory exists in 4 dimensions, another theory exists in 10 dimensions that Maldacena conjectured to be the same, to describe the same object. So this idea is now called holography, and roughly speaking, the object in holography, objects like strings that propagate in extra dimension are equivalent. There is an equivalent way to think about the string as the particle living in 4 dimensions. So a string propagating in higher dimension can be equivalent to particle in 4 dimensions. Okay, there is in Maldaceno's conjecture, there is one important mapping of parameters that I would like to mention here. That is encoded in this formula. So here on the left-hand side, the quantity stay here is the product of the square of the electric charge, of the color charge of the quark, times the number of colors. And this parameter is the expansion parameter in Taylor series. When we try to do quantum field theory using perturbation theory, G square and C is the parameter of the expansion. And that is put into correspondence with the ratio of 2 length scale. The curvature radius of space and the string length scale. But in this formula, there is a very interesting regime that one can take. That is the regime where the coupling constant of the field theory goes to infinity. In this regime, we don't have any perturbation theory because the expansion parameter is very big, much bigger than 1. On the other hand, the string theory, in the string theory, there is a great simplification that happens. Strings now are very small compared to the size of space. So string can now be thought about as point-light object, and the string theory becomes just Einstein gravity. So, an Einstein gravity is much simpler theory to solve compared to string theory. So, this duality that Maldacena gave us became a very powerful tool because it allows us to solve a certain quantum field theory using the gravity dual. Okay, so we want to generalize Maldacena's duality to finite temperature. So at finite temperature, we heat up this stack of ND3 branes, put that at finite temperature, and it turned out that this object is equivalent to a black hole in anti-de Sitter space. There is a very simple way to treat this object in the dual language. It becomes the quark gluon plasma that is obtained by heating up the quantum field theory living in this stack of ND3 brane. Quark gluon plasma is quad because it's not really QCD that we are heating up. It is some quantum field theory living on this in these D3 branes that we heat up is equivalent to a black hole in anti-de Sitter space, and the black hole has a very simple metric that can be written down in one line. Now, we have this correspondence, but we still have to understand how to measure the viscosity using this conjecture. Thinking about the viscosity as the friction force when we move two plates is almost useless here because we have only the liquid, we don't have the plate. So again, we go the theorist way to measure the viscosity is actually the simplest way from the theorist point of view is a different way. The theorist way of measuring the viscosity is to send a gravitational wave through the system. Imagine that we have a neutron star that we can explode and then send a gravitational wave through the fluid. So why is that? Suppose this screen is a fluid, and I use ink to draw a circle inside this fluid, and now I take my source of gravitational wave and send it through the fluid. What would happen is that the circle, in the beginning, would oscillate in shape as the gravitational wave passed by. And there are two ways to think about this problem. Gravitational wave can be thought of as the oscillation of space-time metric. So the notion of length changes. So is the aspect ratio of this circle. Another way to think about this is the usual Newtonian ways. That is, the gravitational wave give you force that pull and push the fluid in different direction and give rise to the motion of the fluid that makes this circle becomes an ellipse. From the second way of thinking, it's clear that there is the motion, there will be absorption of gravitational waves due to the shear viscosity. At the end, we are moving fluid with different velocity at different points, and there is a friction force between different parts of the fluid. And so there is the absorption of gravitation wave is related to the shear viscosity. And that is the essence of Kubo's formula that relate the shear viscosity with the so-called two-point correlation function of the stress energy tensor. Basically, Kubo's formula relates viscosity with the absorption of gravitational wave. So now we have a very good way to use to try to compute the shear viscosity of the field theory on the stack of D3 branes. We have to send gravitational wave through the system and see how it behaves. So if we follow the gravitons, it would hit this stack of ND3 brane and becomes degrees of freedom, some ripple that propagate on this brane. From the point of view of the dual description, what we do here is that we send a gravitational wave to a black hole, and because black hole has an event horizon, some part of the energy of the wave is going to be absorbed by the black hole. And the absorption can be equated on the two sides. So the absorption by the D3 brane, which is related to the viscosity, is equal to the absorption of gravitational wave by a black hole. On the other hand, this problem on the right-hand side is now a completely well-defined problem. It's like the problem of absorption of a black body in quantum mechanics. And so it's mathematically very well-defined, and we can solve that. But actually, the problem is even simpler than that. We can show. So let us recall here: viscosity is proportional to absorption cross-section. For low-energy gravitons. Low energy because in hydrodynamics we want to move the fluid at very large scale. So we send graviton with a very low frequency. Using the Einstein equation, we can show that the absorption cross-section of a black hole for low-energy gravitons is equal to the area of the horizon. If we have a black hole with a size of 3 kilometers, and we send a gravitational wave with a wavelength of 3,000 kilometers toward this black hole, then the absorption cross-section is just equal to the geometric area of the horizon. But on the other hand, the entropy of a black hole is also proportional to the area of the horizon. And that is the famous Bekenstein-Hawking formula for the entropy of the black hole. So now if we take the viscosity, divide by the entropy, in this case the entropy density, entropy per unit volume, of the this quark-gluon plasma in quark, we can show that the area of the horizon cancel out because the entropy is proportional to the area of the horizon. The viscosity is proportional to the absorption cross-section. That is also the area of the horizon. And we divide these two quantities, there is only some numerical factor that remains, and it is just 1 over 4 pi. So the shear viscosity is divided by the entropy per unit volume for this theory that exists on the D3 brane is equal to 1 over 4 pi. Okay, so far we have been using the unit system of theories where h bar and c are put to 1. We can restore the Planck constant and the speed of light in our formula, and we find that eta of s is just equal to h bar divided by 4 pi. So there are some interesting facts here that we mentioned. First of all, there is no velocity of light. Secondly, we have here an example of a theory, this n equal 4 super Mills theory, where we have finite viscosity at infinitely strong coupling. Let us recall that this Mandelsina conjecture in the simplest form works when we take the expansion parameter perturbation theory to infinity. So in some sense, we have the situation where we have an infinitely strongly coupled theory, and the viscosity of that theory is still finite. Its ratio to the viscosity is h bar over 4 pi. And we can show that this ratio obtains the same values in all theories with gravity duals. And that universality is related to the properties of the black hole horizon. And as we have seen in the previous transparency, eta and both eta over S is proportional to the area of the horizon, and the ratio is just equal h bar over 4 pi. It's the properties of Einstein gravity. Okay, so far there is no exception was found in theory with just Einstein gravity dual. Let me just very briefly tell you why the ratio of the shear viscosity and entropy density of entropy per unit volume would have the dimensionality of h bar. It seems to be a very strange fact. Both the viscosity and entropy density seems to have no relation to quantum mechanics, why these ratios certainly have the dimensionality of the Planck constant. So let's go back to Maxwell's formula. Maxwell told us that the viscosity is the product of rho VL, where rho is the density of mass, V is the velocity of the molecules, and L is the mean free path. Now for a gas, to a very rough approximation, the density of entropy is the same as the density of particle numbers. Actually, there is a logarithm, but for this rough calculation, I will put the logarithm to 1. So S is proportional to N, and N is the density of particle, that is the density of mass divided by the mass of the molecules, M, rho over M. So if I take eta over S, it is proportional to MVL. But I can combine MV into the... MV is nothing but just the typical momentum of the molecules. And so it is h bar divided by the de Broglie wavelength of the molecule. And so eta over S is roughly h bar times the ratio of the mean free path with the de Broglie wavelength. And we have done this calculation using Maxwell estimate for non-relativistic fluid, but the same estimate can be done for relativistic fluid, and we get the same result, that eta over S is h bar times the ratio of the mean free path and the typical wavelength of the particles. Now, if we think about this estimate, it cannot be applied when the mean free path is much shorter than the de Broglie wavelength. In order for us to sensibly talk about the notion of particles, they have to propagate over a length scale that is bigger than its de Broglie wavelength. So the mean free path cannot be much shorter than the de Broglie wavelength. It is also clear that the stronger the coupling, the shorter is the mean free path and the smaller is h bar over S. If we push this calculation to the limit of its validity, then we can say that the uncertainty principle seems to tell us that eta over S is bounded from below by h bar times some unknown constant. The mean free path of the particle cannot be much shorter than the de Broglie wavelength. And the theory, it's a very interesting fact that the theories of gravity with gravity dual reaches the value h bar over 4 pi, and that can only be achieved if the mean free path of our particle is at least of the same order of magnitude as the de Broglie wavelength. Okay, now we can now go to a very ordinary liquids like water and ask the question: how does eta, the ratio of eta over S for liquid as familiar to us as water, compare to the ratio eta over S that we have found by using string theory? So here I plot the eta over S for liquid water in unit of h bar over 4 pi as a function of temperature along the saturation curve, that is the curve separating the liquid phase and the gas phase. And it behaves like follow. It goes down, reaches some minimum near the critical point, and then goes up. It turns out that for almost all the liquids that I have looked at, this is a typical behavior. There is a minimum for each substance. There is a minimal value of eta, the ratio eta over S. But for all liquids, for all laboratory liquids, we have eta over S that is bigger than 8.8 times h bar over 4 pi. So all laboratory liquids have the ratio of viscosity over entropy density that is approximately 1 order of magnitude bigger than the value of eta over S that we have found in a class of abstract field theory using string theory. But this is a very interesting fact by itself, that string theory gives us eta over S that is off by only 1 order of magnitude. Okay, so now how one can try to determine the shear viscosity of a quark-gluon plasma. And experimentalists have an ingenious way to determine the shear viscosity of the quark-gluon plasma. They look at collision events that are that at first would seems to be not the most interesting one. The most violent event which creates most of the particles is when two nuclei collide head-on. For the question of shear viscosity, however, it is more convenient to look at the events where the two nuclei that I depict by these two circles here collide with some finite impact parameter. So when the impact parameter is non-zero at the beginning, they overlap. The overlap region is not a sphere, but not a circle, but has a shape that is asymmetric, like an almond shape that is depicted here. And then once this almond shaped region, hot region, was created, it will try to expand. Okay? And experimentally what was observed is that for this type of collisions, there is axial asymmetry in the distribution of particles that was observed in detectors. And the explanation is very simple. Suppose we have a hot region that is has an almond shape like this. When it expands because of the gradient of the pressure. Its pressure tries to push the molecules. But the gradient of pressure is bigger along the shorter direction compared to the longer direction. So the molecules, the particle here would receive a bigger boost in the in velocity compared to the particle here. So we would have the particles that move here would have a bigger energy than the particle would move here. So the effect is actually rather big in experiments. There is almost a factor of 2 difference in the energy of the particles that move here compared to the particles that move in this direction. And it was taken as an evidence that we have created a medium that behaves collectively. Particles push each other. One of the key evidence of the creation of the quark-gluon plasma in the relativistic heavy ion collisions. So, on the other hand, if we have a very large viscosity, this effect would go away. This effect is parameterized by a parameter called V2, the second Fourier components of the distribution of particles. Too large a viscosity would kill this V2, this effect, because viscosity tries to move particles in the same with the same velocities, and they don't like the situation where particles move with different velocities. So hydrodynamic simulation can give us an estimate for this eta, and that's the key observation and used by experimentalists to determine eta. So here is a plot of a recent attempt to determine the viscosity of the quark-gluon plasma by running a hydrodynamic simulation of the quark-gluon plasma and try to match the result with the result obtained in the experiment. So they plot this axial asymmetry of the final particle is as the function of its momentum, and the relevant experimental data are the white dot here, and one can see that if that the best fit to experiments is obtained when the ratio eta over S is equal to either 0.08 in the left plot or 0.16 on the right plot. And the two plots are different due to the different initial condition. We don't know how the profile of the viscosity in the initial almond-shaped regions, and there are two different educated guesses of the profile, and the best fit to experiment is when eta over s is almost of the same order of magnitude as 1 over 4 pi. 1 over 4 pi is 0.08. So first, this hydrodynamic simulation seems to be doing very good job in reproducing the main feature of the data. It's somewhat sensitive to the choice of the initial condition, but one can say that eta over s is at most a few times h bar over 4 pi. So these authors give an estimate for eta over s that is around 0.1 with error, theoretical and experimental error of the same order magnitude as 0.1. But it seems that eta over s is smaller than any laboratory liquid. Let us recall that for laboratory liquid, eta over s is 10 times bigger than 1 over 4 pi. So that Brookhaven National Lab issued a press release in 2005 that the degree of collective interaction, rapid thermalization, and extremely low viscosity of the matter being formed at RIC make this the most nearly perfect liquid ever observed. So let's remember this word, most nearly perfect liquid ever observed. So how perfect is that liquid? A perfect liquid usually is thought of as the liquid with zero viscosity. So nearly perfect liquid presumably is the liquid with very low viscosity. So let us estimate the viscosity of the quark gluon plasma. So we know that eta over s is of order h bar over 4 pi. So we can we know what h bar is, and for the viscosity for the entropy density of the quark gluon plasma, we can estimate it very roughly as the entropy of ideal gas of particle with a temperature of about like 200 MeV, the typical temperature of the quark gluon plasma at RIC. So putting in the number we found and converting the units, we find that it is 10 to the 14 centipoise. 1 centipoise is the viscosity of water, and 10 to the 14 centipoise is even bigger than the viscosity of tar in the pitch drop experiment. It's almost the viscosity of glass in this table. So the quark gluon plasma actually has a very high viscosity. It is not extremely low viscosity, as the Brookhaven National Lab press release may tell you. By low viscosity, actually here they means low viscosity in the sense of the ratio of h bar of eta over the entropy density. And this is a very natural thing to do because the quark gluon plasma and water have very different densities, and to take out the most trivial density factor is to divide the viscosity by the density of entropy. Okay, so the technique of string theory has given us some hints, some very interesting way to think about the viscosity of the quark gluon plasma. We have in 2003, Kovtun, Sarnes, and myself made a conjecture that the viscosity over entropy density for all liquids has to be bigger than h bar over 4 pi. So if that was true, that is very interesting law of nature, and it reminds us of Purcell's question to Weisskopf, that eta, the viscosity seems to be bounded from below. It is unbounded from above, but is unbounded from below. Unfortunately, it is now known that there exist theories where this ratio eta over s is smaller than h bar over 4 pi. There are theories with calculable eta over s, that is 1 minus some constant divided by a big number n. So this inequality that we conjectured in 2003 seems to be not correct. But in the class of models, at least, bad things happen when we try to make eta of S going to 0. For example, in one class of model, something happened, the superluminal propagation start to occur with eta over S below 16 over 25 times h bar over 4 pi. So there is an open question of whether there is and what is the minimal value, what is the real minimum of this ratio of eta over S. And it is a very interesting question to investigate. There is a very interesting more recent work using gauge gravity dualities that tell us new information about the behavior of liquids, that is the chirality in hydrodynamics. So let me mention that work very quickly. Hydrography, that is this technique of mapping quantum field theory into gravity, has helped us discover new effects in relativistic hydrodynamics. That is, that this effect has been overlooked in all previous treatments, including the textbook of Landau-Lifshitz that Shiraz mentioned. And this is can be thought about as chiral separation by rotation, that I will tell you a little bit in more detail later. But this I will just mention here, that this effect has deep connection to quantum anomalies, with Chern-Simons theory and a lot of geometry behind quantum anomalies. And it was observed first, I think the first indication that the previous treatment of hydrodynamics was missing something was made in 2007 by Shiraz Minwala and collaborators. And then in a series of subsequent papers, it was shown using holography that this effect must exist in a class of theories with in fluids with anomalies, and it is the result. It can be thought of as the inescapable consequences of quantum anomalies and the laws of thermodynamics. So here is in picture what happens. What is this effect? So let us recall that QCD. Consider an idealized version of QCD with massless quarks. The U and D quarks in QCD are almost massless. So if the quark is massless, we can classify the quarks by saying whether it's a left-handed or right-handed. A left-handed quarks would have spin pointing to the opposite direction, and the right-handed quark compared to the direction of motion, and the right-handed quark with spin pointing to the same direction as the direction of motion. And we can think about the conserved chiral charge, that is the number of left-handed quarks minus the number of right-handed quarks. That would be some quantity that is conserved, and we can talk about the current of this charge. This current, usually in hydrodynamics, a current contains two parts. One part is the convection part, and another part is the diffusion part. There is two ways that if you open a bottle of perfume, that you can hear perfume from afar. One is by diffusion. Another way, when someone walks around the room and there is a convection. In this example of QCD with massless quark, it turned out that there must be another part of the current that was missed in all previous treatment, that is the vorticity-induced current. So what is this vorticity-induced current? Let's imagine the following situation, and to make the effect clear, I will use an analogy. Let's take a cup of water, and then pour sugar into it. Sugar has two chiralities: the left-handed sugar that we cannot digest, and right-handed sugar which we can. So we put sugar in. So this is the molecules of sugar. This is the right-handed sugar, and we rotate this cup of water. Okay, so if the sugar behaves like quarks in quark matter, the left-handed sugar and right-handed sugar would try to drift in different direction. This effect would exist. Quark would separate in a rotation, but sugar would not. And this effect is deeply related to quantum anomalies, found by work by Shiraz, Minwala, and collaborators, and subsequent works. So holography has also been useful in order for us to discover new interesting fact about hydrodynamics. So let me end this talk by quoting from Chandrasekhar. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their constructions are our concept of space and time. And what I want to to speculate at the end of this talk is that the perfectness of the matter created in the heavy ion collisions in the quark gluon plasma that Brookhaven created in Brookhaven National Labs, that seem to have to flow with almost like a perfect liquid, it might be related to the perfectness of black holes. That was the topics of the long period of research by Chandrasekhar. Thank you very much.
Thank you for a brilliant talk. Take a few questions.
You know, one of the ways of measuring the viscosity of a liquid is to take a long tube and put a pressure difference across and see how much fluid goes through.
Yes.
Would that be consistent with the a measurement of that type instead of dissipation? Would that be consistent with the kind of bounds on the viscosity that you get?
I think if the tube is if the Reynolds number is low, yeah, then one can measure the viscosity of a liquid this way, and it would be the same viscosity as measured in the friction between two plates, and also it is the same viscosity that is measured by absorption of gravitons. So it's the same. It would be consistent. Oh, yeah. The viscosity, if superfluid, is a more subtle notion that I did not mention here. For superfluid, to measure the viscosity of the normal component, we have to do the Andronakashvili experiment. That is, we have two plates and then move one plate with respect to the other to excite the normal component. So I checked for the normal viscosity of helium-4 measured that way, and it is the ratio eta over S for superfluid helium measured in this experiment is consistent with it being bigger. The ratio is bigger than h bar over 4 pi. Yeah.
Isn't the fact that you take the superfluid has zero viscosity and the normal component has finite viscosity, and one is kind of sloshing over the fact that the actual viscosity as measured turned out to be quite low or zero?
Okay, so the viscosity would, if one measured by the absorption of gravitational wave, would be the normal phase viscosity. The normal the superfluid component has zero shear